All right, welcome back. Today, I thought we're going to continue our QuadTree project, and I thought one quick improvement that we can add is to have a GUI which shows what the QuadTree structure actually looks like. So if you remember from the previous video, we had a QuadTree structure that looked like this. This was a representation of a QuadTree for point data, which is very similar to what we've built. So I thought it would be nice if we were able to build something like this out and actually show where the QuadTree is actually subdividing and where the points are being added to the QuadTree and how the QuadTree subdivides when you fill the quota for the number of points that you have. And a very simple way to do this in C++ is using a graphics library like SFML. SFML stands for the Simple and Fast Multimedia Library, and it's a really good library to essentially plot a window and get some basic shapes on there. It's not really too difficult to use, and it doesn't require any fancy graphics libraries or graphics or any GPU sort of processing. It's meant for very simple, just rendering basic shapes onto the screen. So we're going to be using this. It is multi-platform. You should be able to compile this on different applications of choice. I'll be using the Linux machine here. So it's, for example, on Debian or Ubuntu, it's easy to install the SFML development library. And once you write it, once you write your code, you just compile. You just link against these libraries that you have. So with that said, let's go ahead and get started. The main loop for rendering to a window is to just create a window of a given shape with a given title, like so. And then you have a loop while the window is open. So as long as the window is open, it's going to keep running everything inside this. You should ideally poll for a event. So for example, if you click the close button, you should actually handle the closing of the window over here. Otherwise, your loop will run forever. And then you clear the window to basically reset it to the background color. And in between this and the display, you put in all of the drawing that you need. So all of the shapes that you want to draw, all of the lines, so on and so forth. And then once you're done adding all of the elements to this window, you display it out, which will actually render that and then update the window. So within this loop, the window is essentially being redrawn, and all of your calculations, all of your physics will happen inside here. Okay, with that said, let's go ahead and get started. So I'm going to add the SFML graphics.hpp library. So let me just move this a little bit out of the way. By the way, just to show you where we were from last time, so we had a QuadTree where we're inserting a bunch of points. Let me just really quickly compile this again. We had a bunch of warnings because of the conversion between integers and long, for example. So we're going to ignore that for a second. And then if I run the QuadTree out, it's essentially saying these are all of the points that we have added. And since we're running 100 points, we're adding 100 points, and then we set our capacity of each node to be of size 50. It's actually subdividing the QuadTree twice and adding all of these points to level 2, where the first level is level 0 and it goes down to level 2. So here's our 100 points that we've added. We essentially incremented this by x to be 1 over 4, I over 4, for I going from 0 to 100. So it goes from 0 to 25 in this case. So what we want to do is to essentially render these 100 points onto the screen. So if I just pull up the documentation again, so what we want to do is to copy over the graphics library, like so, and also copy over the window. So let me add the window after we've added all of the points. So we don't want 200 by 200. Let's do something a little bit bigger. Let's do something 600 by 600. And then we'll call this the QuadTree. And then in here, we want to do while window.isOpen. This is where our loop lies, and this is kind of where things deviate. So instead of doing the polling for the event in that way, I'm going to change things around a little bit and define a event. And then what you're going to do is essentially poll for this event now. So while window.poll event, and then we're going to apply this to the event over here. And if the event.type equals closed, this is basically telling you that the window has been closed. We're going to close the window. If we're not doing a closed window, we're going to clear the screen and then display it. So let's compile this, and this should give us an error because the SF library is undefined. So what we need to do is to actually link this against the SFML library. So this is the SFML graphics that we need, and SFML window. I believe that's correct. Those two are what you need, graphics and window. So let's try this out. We also need the LSFML system. And that compiles without a warning, without errors. It gives us a few warnings, which are the same warnings before. So now if I run this out, so here's our window. It just says QuadTree on it. There's nothing displayed in this window right now because we haven't actually drawn anything to the screen. But this all works. So if I close the window right now, my command should exit. So let's do something very simple. Let's create a square. And just looking through the documentation on how to display this. So what we're going to do is let's create a square or a circle. So in this case, let's just create a circle shape. The input here is the, let's just look this up to make sure I'm saying this correctly. If I go to the documentation, so if I look for a circle shape, you should be able to define multiple parameters here. So the circle shape takes in the radius. So that's basically what you're putting in here. So I'm just going to copy this over right now. And ideally, I should be able to set the position through set position, if I remember correctly. Let's set position. Yep. So I should be able to set the position of this object, and I should be able to move things around. But for now, let's just add it to the center of the screen. So I'm going to create a circle of size 100 units, 100 pixels in diameter, and then the shape dot set fill color. We're going to set it to SF color. Let's do a red color. And you can do this with window.draw shape. And if I compile this and run it again, I should be able to get a, let me just move this over. So I should be able to get a red circle of radius of units 100. Let's try to move this around a little bit. So let's say we want to move the position, and for this we use a vector to f. Oh, I see. So you should actually be able to set it to just x and y. Okay, let's do that. So let's set it to, our window size is 600 by 600. So let's set the window to position to 300 by 300. If I do that, I should get, basically what it's doing is adding the top left of the rectangle of the circle to the locations of the top left to the center. And so this is shifted up over by a value of 50 pixels, basically. We should be able to set the anchor point. So we should be able to set the local origin of the object. And if I do that, I should be able to say that the center of this pixel of this circle should be the center of the actual circle. So let's try to do that. So shape, let's do this before we set the position. So shape.set origin, and this is going to be 100 by 100 because the radius is 100. And if I rerun this, I should get the circle exactly in the center of the screen. So now we know how to add objects and move things around. Let's start by essentially drawing out our quad tree. And to do this, I'm going to remove all of this. Let's remove this. So what I want to do is to actually create a render method. So let's create a render.h. Oh, not that. Let's create a render.h where we're going to create all of our functions for rendering. Like so. Let's import. We don't need this. Let's import our graphics library. Like so, and let's include also our quad tree so we have access to the data structure for it. And then let's do a void function, which is render QuadTree. And this is going to take in a window. I believe I need to pass the window in as a pointer, and then we'll also pass in the QuadTree. Yeah, okay, so that's fine. And then let's also create a render.cpp, and this is going to include the render.h. And then here we'll actually define our render QuadTree, which is the I actually don't need a const for this. Actually, let's swap the order of these parameters. So we pass in the window last. So this is going to be the const QuadTree, which is the object, and then the SFML window. Okay, so now we have a rendering function. Let's start to add stuff to this. So what we essentially want to do is to take every single box in the QuadTree, or essentially draw the box of the QuadTree, right? So we know that let's just map this out. So we know that the xmin, or let's just do the bounds, right? So the bounds is the qt.bounds, right? We'll clean this up later. I just want to kind of map out what we really want to do. So what we want to do is to create a rectangle where this is defined by, let me look up the rectangle shape really quickly. So we had the circle shape. Let's try to define a rectangle shape. I do believe we should be able to set, okay, yeah, let's just do it this way. So we define a rectangle, we set its size, outline color, thickness, and so on. And then we also set its position, which again, remember, is one of the corners. So let's just define a rectangle here. And then rect.setSize should be to f, which is going to be just the the bounds dot width, the bounds dot height, right? And then the location is just going to be the bounds dot xmin and then bounds dot xmax. Let's set the outline color to be white. And then rect set outline thickness to be 2 pixels, right? And then we can just do window.draw. I see, it's a window draw rect. No, that doesn't make sense. Oh, I see. It's not a SF window. It should be an SF render window. There you go. That should work. So this is only going to draw the top level QuadTree, but what we really want to do is for leaf in QuadTree.leaves, we want to essentially recursively call leaf and then render it onto the same window. This might be because this is an array, so there are 4 leaves in any QuadTree, so we should just be able to render each of these leaves like so. No viable conversion, const value type. I see. So this is a pointer. So we should be able to do something like this. Yeah, there you go. So the qt.leaves is a pointer to the actual leaf node. So we need to pass in by reference. Actually, I wonder if it's actually going to be easier to pass by reference everywhere. And this is asking for a pointer, so we just need to get. Great. So if I call this here, I should be able to render QuadTree, and this is going to be the QuadTree, and then this is going to be the window, the pointer to the window. And this should be porting render. Great. So let's try this out. This might give us some undefined, yeah, because I'm not actually compiling this. So we need both this and the render.cpp. Undefined reference to render. Because this should also be render window. So let's clean this up. This is annoying. I might just be doing something really stupid here. Let's just remove all of the other warnings really quickly. I should be able to just, okay, QuadTree.cpp, render.cpp. The linker is having issue finding, do I have to swap the order? I shouldn't need to. Did I? Oh, I see. This is really stupid. Okay. So these are both pointers. And then here I did this wrong. So this should also be a pointer. And that should render without issues. Okay. So if I run QuadTree now, oh, something was a seg fault. Let's try to see what's going on. Let's print out. Drawing QuadTree. And let's just print out the bounds. Let's actually remove this print points because we don't need it anymore. We don't need the counter anymore. So it's drawing QuadTree 0, 0, 25, 25. It's failing in the second round for some reason. Oh, I see. This is we should make sure that this is divided. So if qt dot is divided, otherwise it should not try to render a subdivided QuadTree. There we go. So it's continually drawing. That's why you see these the repeated message. But essentially, this is where our QuadTree is. The issue here is that this is a 600 by 600 pixel wide box, and we're trying to render something that is 25 by 25. So that's where the issue is happening. So let's close this for now. Let's remove this. So basically, what we want to do is to devise a scale. So rather than treating this as the absolute value of the scale. So what we could do is to set this to 25 by 25, which would make this a very small window to actually observe. So what we want to do is to actually define a scale. so that we're actually able to render things within that scale. So we want this 25 by 25 window to match our 600 by 600. And the way we do that is to set, so let's do it this way. Let's create a double scale, right? And we define it here. And so our scale is essentially going to be 600 divided by 25. We should make all of these sort of okay. So we should ideally make all of these configurable properties, but for right now, we'll just keep this as it is. And so when we go to render.cpp, we should be able to essentially multiply this by our scale. And since we're starting and ending at 0, we'll add a padding in a little bit of time, and we'll add a transform function. But for now, we just want to render this to scale. And I don't think we need to set a fill color. That should be handled automatically. So let's try again with our new scale function. I think it's automatically also setting the fill color. So let me check this to be sure. So just looking through the documentation, we can use transparent. I see, the shape's fill color is opaque white. So we should set this to a transparent, or we should set it to black. So let's set it to transparent. Set fill color transparent, like so. There we go. So now we have our quad trees being rendered. You can see there's a little bit of overlap here, which is fine. But basically, this is where our quad tree is sitting. I think what we're actually missing is a global quad tree because we're not adding any padding. So let's add that padding first, and let's come back to this. So let's create first a transform function. Transform to view. And we basically want to take in a position. And we want to return a new position, actually. So essentially what we want to do is to take in a position in our world space, which is between the 0 to 25 on the X and Y. And we would want to return something that's in our pixel space, which is 600 by 600. So we already have the scale over here. Let's just create a few constant values. So let's create a padding, which is, let's say we have a padding of 10 pixels on all sides. And so in our case, our scale is actually going to be 600. Actually, while we're here, let's just set all of this. So int so we're going to set our window width and window height. Default function. Okay, let's just set this to an int. Window width and window height. So let's set our window width to be 600 and window height to be 600. And we're going to assume that these are both equal for now, because it gets too complicated if you want to do things differently. So now what we're going to do is to cast our window width minus twice the padding divided by the bounds dot width. And this should give us the actual scale that we're working with. And so our transform function is going to take a position in our world space, so the 0 to 25, and going to let's convert this to transform to pixel space, just to be extra clear. So what we want to do is to take in a position in the 0 to 25 by 0 to 25 space, and convert it into our 0 to 600 by 0 to 600 space, right? And so essentially what we want to do is let's define our new x and y. So x is, I'm going to write this out explicitly and we can condense it later on. So position dot x, then the y is position dot y, and our new x, new y is going to be x, new x equals x times the scale plus the padding. And then the new y is going to be y times the scale plus the padding. And the reason why this is the case is we're going to add, basically the 0 is going to be at this padding point. And then after that, it's going to be scaled based on the scale. And then the final value, the position of 25 should match 600 minus the padding. So what we want is 0, 0 should be mapped to padding by padding, right? And then 25 by 25 should be 600 minus padding by 600 minus padding. This is the transformation that we need. And so now we can just return a new SF vector 2f that basically takes in this new x and this new y. And so here, rather than setting the position here, we should just transform to pixel space of SF vector 2f, and this is just going to be the bounds.xmin and then the bounds.xmax. Right, so we don't need to worry about the size because the size is automatically calculated from the scale. We just need to transform the bounds, the position. So let's try to render this out. And there we go. So for some reason, this is wrong. The box is being rendered down here. So there's something really wrong with how we're doing this. Oh, I see. Bounds.xmin, bounds.xmax. No, this should be bounds.ymin. Okay, let's see if that works. Clear the screen. Oh, just run that again. And there we go. So we have our basic quad tree out here. And we have our subdividing surfaces over here, like so. And then every time we subdivide, we're getting into smaller and smaller. So this big tree, this big box over here is level 0. Each of these these smaller boxes is level 1, and then this smallest box is level 2. So once we plot out the points, we should actually be able to see why we're only creating this over here and not seeing any points emerge over here. So let's close this, and our next step is to actually render the points. But let's come back to this because we actually need to figure out how to render these points. What we could do is two things. One is probably the right way for rendering things is to actually create a global list of points that are being added as unique pointers to our quad tree. And that way, like the main program is actually keeping track of where the points are, which points are being added, but regardless of whether it's added to the quad tree or not, which is the right way because if things fall outside the quad tree, you still need to know where the locations of these points are. The hacky, simpler way is to actually just render these points directly from the quad tree. So loop through the quad tree, loop through each of the leaf nodes, and then render all of the points in there. Let's do the hacky version for now. And then we'll come back and actually fix things. So I'm not going to touch this render points function. I'm going to put this all on inside the render quad tree. So we have the Qt is divided, and then and then for auto the point in the points, we're going to render this as a point. So this is going to be a circle shape. Point circle, and then what we're going to do is to essentially set the position So let's create this as radius 5. Maybe it should be a little thicker than the outline. And then we'll set the position of this to be, remember we need to transform the function again. I need to do this. Transform to pixel space, and then this is going to be an SF vector 2f, where the position is the point dot x and then the point dot y. There we go. This should be, oh, I see. So this is a pointer, this is a pointer, and that should work. So now we're plotting each of these circle shapes as points. Let's just set a color to these. Set fill color. Let's set it to blue, maybe. Let's do that. It renders without any problem, and let's see what happens. So none of my points are appearing, which is a little strange. So we're setting our point circle. Oh, I see. We're not actually rendering these to screen. So the last step is to actually window draw, and we need to add these point circle. So there's a lot of ways to optimize this. So rather than essentially doing all of this first, you should be able to actually create a list of circle shapes and then plot them all on the screen. We're going to skip those optimization steps right now because we just want to get things working. And then once things are actually working, we'll start to think about performance and so on. And there we go. There's our list of points. And the reason why they look like this is because if you look at how we're adding these points, we're actually adding them to an x value that increases with our increment by 20. And in this case, we're actually counting in computer vision. We actually count from the top of the window going down. So y equals 0 corresponds to this, and then y equals 25 actually corresponds to the bottom. So we're adding it essentially 4/5 of the way down the screen, which corresponds to this location. Well, between here and here, it's 4/5 of the way down. And so the QuadTree is actually creating two sets of iterations, two sets of subdivisions. So the one is the main box, and as it adds more and more pieces down here, it has to subdivide this main box into these 4 quadrants. And as it adds more points to this level 1 quadrant over here, it needs to further subdivide this quadrant and creates 2 smaller quadrants. So to see how the QuadTree actually works, let us actually add points on the fly, and then we'll capture mouse input. So as we click, we should be able to add points to the QuadTree, and then see how it updates in real time. So let's stop. Let's remove the points that we have so far. If we render this out, we should actually see just an empty box. So there's nothing in here. There's just the empty QuadTree. And then we need to capture a mouse input and convert that mouse input location to your pixel space so that you're adding a point at that pixel space. So let's try this. Event mouse button pressed. I need to look up the documentation on this real quick. Oh, something is wrong with the search. Let's go back. Okay, so this is a mouse button pressed event, and basically we should be able to capture the position of this thing. Let us really quickly see how to use this. If I go to, I believe the tutorial should be here. Yeah. So if I go down to window management, events explain, so keyboard, mouse, and joysticks. So these are if key events are pressed. Right, so basically if the mouse is pressed, we should be able to get the position of the mouse inside the window or global position. So let's try to get the mouse position inside the window. So Okay, let's do it this way. So SF mouse is button pressed, SF mouse left. So if we click the left button, we should be able to get the mouse position equals SF mouse get position inside the window. I believe it shouldn't matter if it's a render window or a window. Yeah, it shouldn't matter. So what we should do is also create a, let's just print this out to screen. So let me close this. So let's print this out to screen every time we do get a mouse event, mouse pressed at like so, new line. And then this is the mouse position dot x and the mouse position dot y. So let's render this out. And so if we click here, we should be able to get, so as you see, this is the lower point, and then this should be roughly 600 by 600. And so the issue is that we could keep clicking the mouse and we'll keep adding new event. So this is one of the events with, one of the issues with how the way we're doing it right now, which we're just checking for is the mouse button pressed. So we should actually be checking for if the mouse button is released, we should get the position of the mouse cursor. So let's look for that. I believe there should be a different there should be a different method for checking if the mouse button is released. Or maybe we can check for an event where the mouse button is released. Oh, maybe just the event. Mouse button released. So we should be able to check the mouse button released. This should be... Okay, ideally we should also be able to get whether this was the left click or the right click, but for now let's just do event.type equals SF event mouse button released, like so. So let's try this out. And this should essentially, we should not be able to get anything happen when we click, but every time we release, we should get a an event over here. So the issue is that I'm doing a right click right now, that still works. If I do a left click, that still works. But if I move my mouse around while holding down my click button, it shouldn't actually do anything. And this, since we're getting stuff relative to the window, it only works if you're inside, if you're focusing on the window. But the positions still work. This is about 600 by 600, and then this should be about 0 by 0. So all of that works. We should be able to just add in our points now. And to do that, so we have our mouse position, and now we need to convert this into a the world position. So we have our pixel position, which is between 600 to 600. Let me just delete this. And then over here, we should be able to, we need to convert it to our 25 by 25 pixel. So let's, in our render.cpp, let's add a new function. So we want to return out a vector to f by transforming to world space. And we want to pass in a vector to I in this case, because we know that the coordinate, actually this should be a vector to I as well. But that is probably fine because this takes in a vector to f for the position. So let's create our vector to the transformation back to world space, which is exactly the opposite of this. So realistically, we just need to do sf vector to I, and then we want to static cast int our position.x minus the padding divided by the scale. And let's worry about overflows and rounding errors later on. Let's just get a simple static cast int, and then this is position.y minus padding divided by the scale. I think that's one too many. Return type to vector2. Oh, I see. This should be vector2i. There we go. So our x position is going to be the position that we input. Oh, I see. That's wrong. I see. I have completely messed this up. So this should be a double, and this should be a double. And we don't need to convert everything. We just need to convert this. And then we'll put parentheses around here. What's going on? Right, that should work. Okay, so now we should be able to transform to world space. So we should be able to get SF vector to F. The point position is going to be transform to world space. Probably just as in transform to world space. I see, because we haven't created. Let's just really quickly do that here. Vector to F, and then this is transform to pixel space, and this takes in a const SF vector to F, and then transformed, world space, and then this also takes in a const vector to I. That's correct. So here I should be able to take, yep, there you go. And then this takes in the mouse position, and then I should just be able to create a new point. Let's create this as a, I remember we had this problem before, so new point, and this is going to be a point position dot x and point position dot y. Again, this is probably not the best way to do it. We should use a unique pointer, but again, we'll do all of those optimizations later on. And then this is just a qt.insert point. So right now, let's try to see if this works. So we have a quad tree with no points in it. If I add a point, here you go, it's created a point. And as I add more and more points, it should eventually work. So we set the capacity to 50. Let's reduce it and let's see if it's actually subdividing. So in my QuadTree.h, let's set the capacity to a value of 5. So every 5 new ones that I create, it should subdivide. So 1, 2, 3, 4, 5. There you go. It's subdivided it. These two have 2, and so it's not subdividing. This one has only 1. The blue is actually really hard to see. So let me quickly change that. Let's also set this to. I don't know if I can set like a different color. Let's just set it to a white. So that's easy to see. And I'm going to reduce the size. Maybe 3. So now I'm able to add points, and you see that it's actually subdividing as we go. So here, let me start to add 3 more points, and you see now it's filled up the 5, so it's actually subdivided even more. And then if I add a few more points, it'll keep going. It'll keep going as we add more and more points, and like so. And it can keep doing this regardless of what's happening in any of the other. Oh, you can see it's starting to get a little laggy right now as we're adding more and more points. It's not able to actually like keep up with how quickly we're adding points. So this is actually one of the performance issues that we need to sort out. But now we have a way to render this quad tree out. We're actually able to see where things are being added to the quad tree. So let's work a little bit on optimizing this structure and cleaning up how we do things. Okay, so now that we have the graphics rendering done, let's try to optimize things a little bit. So rather than actually having the points defined like so, let's create a version where Rather than storing these points as a list of pointers, let's try to create shared pointers instead. And the benefit of a shared pointer is that we will essentially create the points in our main loop over here, but the QuadTree will have access to those points. It'll basically share access to those points when we're able to add it into it. But the main ownership of those points will be actually in the main loop. So let's do that first. So let's create a vector of shared pointers of points. And this is going to be our list of points, essentially. And then in our QuadTree, we also want to move this to shared pointers instead of pointers. And then here, we also want to do the same thing. So now our insert function is able to take the shared pointer in. It's going to insert it to here, and what the shared pointer is going to do is it knows that the location of this is basically shared between multiple data sources. So one of them is the QuadTree, and the other one is where it's being defined, which is over here. And now we need to update this method when we're adding new points. So instead of doing a new point, we want to create a shared pointer of a point, and then instead of defining new, we're going to make shared. This is a point, like so. So once we do this, the point is going to be created here, and we're going to insert it into our. Actually, we can do this in one loop. So we can just do points dot insert. Yeah, we can do points.insert pushback. Points.pushback, and then we can just do something like so. So essentially, in each loop, we're checking for the points that we created, and once it's created, we create we add it to our global list of points that's over here, and then we insert it into our QuadTree once we actually have these points. And so right now, rather than rendering things with the QuadTree like so, rather than rendering the points here, we can move all of this to a new render points method. And this is going to take in a vector of shared pointers type point. This should be a const, actually, because you don't want to update this vector. And let's paste what we had here. So for point in points, oh, and this also needs the SF render window. There we go. So nothing has really changed from what we did before in terms of performance. We're taking our QuadTree, we're adding the points to it, and then we're rendering both the QuadTree, and we need to also render the points. So let's create a new render points function, which takes in vector of shared pointer of point. I'm sorry, this is a const. And then so did I mess something up? Probably did. I think this is I'm missing this. There we go. So it takes in a vector of shared pointers, and it takes in the render window. So if I compile this, I'm not seeing any major issues. This is still the same warning from before. Yeah, this is still the same warning as before. Let me just really quickly fix this. Int move points to this is size, and that should fix that issue. I see. I don't actually need this. Right. That's a problem that we have, but that's probably fine. And now our QuadTree, it should still okay. It's not actually adding the points. Why is that? Let's see if we're actually adding points correctly. And then let's also print out the size of points. I keep mixing up fprintf and printf. Now there are, what is the issue? Let's render this out. Okay, here's our window. So there are points, and it's putting them in the right place, but for some reason it's not up. I probably did the same stupid mistake. No, I did. Oh, I see. I need to actually render the points. So render points, and this is the points and the window. No matching function. Window pointer. So let's remove. Let's keep that. So we have our window. Yep, there you go. We're now able to add points. For some reason, it's not actually subdividing. Oh, I see, because I changed the capacity, but 50. Let's set that to 5. There you go. Now we're getting the subdivisions that we wanted. The performance is still pretty awful. You can see it's lagging when we're adding more and more points. We can figure out whether that's from the QuadTree or that's from the rendering. My guess is that it's actually from the rendering. Okay, so we have a list of points. What we should do now is actually optimize this a little bit. And we can do that by actually rendering the circles that we have as a polygon. Or maybe circle array. If I understand correctly, a vertex array. That's right. So a vertex array essentially takes in a number of vertices, essentially. So you keep adding the number of points that you add as these positions, and then you just render them at the very end. So let's do this. I should actually check the documentation really quickly for how to do this. So SF. So shapes. So that's a circle. That's the outline. So we've been rendering normal circles so long for all this time. What we want to do is vertex arrays. Right, so this is actually what we want. We want to be able to actually just do a set of disconnected points. So we can create a vector of vertices and then display them as not as triangles but as points. So let's try to implement this. Right, so let's try to do this. So let's do and this is our vertices. And then what we're going to do is we don't need these anymore. So vertices dot push back, and this is going to be our new vertex. And then we're going to draw window.draw. This is going to be our vertices data, and then vertices dot size, and then this is going to be our primitive type of points, like so. I believe you should still be able to set the color somewhere. Let me see. So if I look at the vertex array, I should be able to set the color of this automatically. I see. So I should be able to add. Okay, yeah. So let's try to do this. So our vertex is actually going to take in 3 properties, which is the position, like so. And I believe that should be it. So if I try to run this, I'm not getting an issue. And here is our, yeah, there you go. So we are getting our points to draw. And it's a little bit faster in terms of actually rendering this to the screen, but I think we're still seeing some performance hit when we get to really high numbers for doing the subdivision of the QuadTree. So let me reduce the size of the QuadTree outline really quickly, so we should actually be able to see what's happening here. There you go. We're actually able to get the QuadTree to subdivide pretty quickly. So there is an optimization step that we're still missing for the actual QuadTree, but now we're actually able to get a QuadTree that's rendering and that's displaying the number of points that we have, and showing us where the points are being added. So with that, I think that's where we're going to stop today. And in the next round, we're going to take a little bit of a look at optimizing this and then adding some interactivity in order to see if we can actually add and remove points from the QuadTree dynamically. So until then, 1-0.